Hello everyone, my name is Nitin Sever. I'm a PhD scholar at IIT Madras. Today I'll be demonstrating the process of quantum efficiency measurement. External quantum efficiency measurement is a key parameter used to evaluate the performance of a solar cell. It indicates how efficiently the device converts incident photons to electrons at each wavelength. The external quantum efficiency or EQE measurements refers to the ratio of the number of charge carriers collected by the device to the number of incident photons on the device at a specific energy or wavelength. It accounts for the losses, including those from reflection, the absorption by non-active layers, and other processes that do not contribute to the charge generation. The figure below shows a typical EQE spectrum of a solar cell. The golden line represents the ideal quantum efficiency. However, in practical scenario, various losses occur. In blue region, the losses are primarily due to the surface recombination. In the red region, losses arises from the rare surface recombination, the reduced absorption at lower wavelengths, and limited carrier diffusion lines. Beyond a certain wavelength, the EQE drops to zero due to the lack of photon absorption. The figure illustrates the schematic of a EQE measurement system. The main components of the system include a light source, monochromator, optical chopper, reference photodetector, beam splitter, solar cell under test, lock-in amplifier, current voltage measurement system, data acquisition software, and a computer. The light source provides a broad spectrum of illumination, typically ranging from UV to NIR region, approximately 300 to 1200 nanometers. A combination of xenon and quartz halogen lamp is commonly used for this purpose. An optional bias light is used to simulate sunlight, helping to maintain the solar cell in a state that closely resembles actual operating conditions. This is particularly important for the devices that exhibit nonlinear recombination dynamics or trap filling effects. Bentham 605 current stabilized power supply units are used to power the lamps, ensuring consistent and stable light output during the measurements. The monochromator selects a specific wavelength from the broadband light to illuminate the solar cell. It uses diffraction gratings or a prism to disperse the white light into its component wavelengths, allowing only a narrow band of light to reach the sample at any time. In our system, a Bentham TMC300 monochromator is used to select specific wavelength of light for EQE measurements. An optical chopper modulates the light beam at a known frequency using a rotating disc with slits, creating a pulsed or chopped light signal. This modulation enables the system to distinguish the photocurrent signal from the background noise. The reference photodetector measures the actual power of the incident light at each wavelength. Typically, silicon or germanium detectors with non-quantum efficiency are used for calibration, allowing accurate calculation of the photon flux. A lock-in amplifier is employed to detect the weak photocurrent with high sensitivity and low noise by locking into the modulation frequency of the chopped light, effectively filtering out unrelated noise. This is the sample stage of EQE measurement system. The conductive stage is designed to mount bottom contact devices, particularly those with top illumination configuration, along with manipulators for precise contacts. Crocodile clips of this types are used for third generation solar cells that requires illumination from the bottom side, allowing for flexible and reliable electrical contacts during measurements. The working of a EQE measurement system can be briefly described as follows. Light from a broadband light source passes through a monochromator to isolate a single wavelength. This monochromatic light is directed to a solar cell, generating a small photocurrent. A reference photodetector measures the intensity of the incident light, while a lock-in amplifier extracts the photocurrent signal with high sensitivity. The computer then calculates the EQE by comparing the measured photocurrent to the photon flux at each wavelength. This process is repeated across the spectrum to map the solar cell's EQV. The key precautions before starting the equipment are: allow the light source to warm up for at least 15 to 30 minutes for a stable light output. Avoid vibrations, temperature fluctuations, and ambient light leakages. Perform measurement in a dark enclosure to minimize the noise. Ensure all components are well aligned. Use the required personal protective equipments. After confirming all precautions are taken care, turn on the main power supply. Switch on the bias lamp and the xenon lamp. After turning on the xenon lamp, wait for the lamp failed indicator to turn off. This indicates that the cooling system and the xenon lamp is working properly. Once the lamp fail indicator goes off, turn on the quartz halogen lamp. Then switch on the monochromator. Turn on the detection system and the lock-in amplifier. Finally, power on the computer and launch the BinWin software, which controls the equipment. Once the software launches successfully, select the DC mode configuration. Before starting the actual measurement, confirm the system is calibrated using a photo detector with a non-quantum efficiency. To ensure light is properly falling on the photodetector, set a specific wavelength, 555 nanometer, which corresponds to green light and visible to naked eye. Click the Go to Wavelength option. A green light spot corresponding to 555 nanometer should be appear. Mount the photodetector in the slot near to the substrate stage and connect it to the detection system using BNC cable. Adjust the photodetector so that the green light spot falls exactly at the center of the photodetector surface. After completing the alignment, close the chamber. In the BinWin software, navigate to the Scan Setup menu and ensure the data correction is disabled. Set the scan rate from 300 to 900 nanometers with a step size of 2 nanometers. Click the New Scan option to begin the measurement. During the calibration step, ensure that the y-axis of the graph displays signal in nanoamps. A graph will be plotted across the specified range with the chosen step speed. Once the calibration curve is available, use the Save to File option to save the calibration file with .ben extension. After saving, go to the Scan menu and select Data Correction. Ensure that the certificate file selected is the standard silicon certificate file and the system file is the one saved in the previous step with .ben extension. Click Calculate Calibration Data and then press Yes to confirm. This file can be saved with .cal extension. The system is now ready for actual measurements. Go to the Scan setup and open the Advanced mode. Ensure the data correction is enabled now. Click the New Scan to begin the actual measurement. Once the measurement is finished, to analyze the results, go to the Analysis menu and select Quantum Efficiency to generate the external quantum efficiency versus wavelength curve. Now, we will measure the EQV of the perovskite solar cell fabricated in our lab. The device is made in NIP configuration with 6 devices on each substrate. The top metal contacts of each device are extended to the left and right sides, and the bottom FTO layer is connected to the long gold pads located on the bottom and top edges. To characterize this type of solar cells, crocodile clips are used, as mentioned in the beginning of this demonstration. These clips are used to connect to the top and bottom contacts, and the connection is completed using a BNC connector to the detection unit. To ensure the light spot is precisely aligned with the active area of the perovskite solar cell. Once the alignment is confirmed, we return to the scan setup. Make sure that the start wavelength, end wavelength and the step size are properly set. Now start the new scan. Once the analysis is finished, the data can be saved using the file option. It can be exported to the required extension using the export option in the file menu. The external quantum efficiency can be used to calculate the short circuit current density or the JSE of the solar cell. To do this, integrate the product of the EQV spectrum, the incident photon flux, and the elementary charge over the measured wavelength range. From the figure, it is evident that the maximum EQV occurs between 450 nanometers to 500 nanometers. And the JSE calculated from the EQV is 18.38 milliamps per centimeter square. This value can be used to verify the JSE obtained from the IV measurement of the solar cell. Once the measurement is finished, close the Penguin software and turn off the computer. Now switch off the detection unit and monochromator followed by lamps. And finally turn off the main switch. With this, we are concluding the demonstration section. Thank you for watching.